Hey everyone, today in this video we're going to talk about topics 5.8 and 5.9, which are very similar. We're both going to be talking about sketching graphs of functions from their derivatives and then sketching graphs of derivatives from their functions. We're going to connect a function, its first derivative and its second derivative together via graphs. Okay, there's not really a lot of notes to talk about here. Basically, we're just going to jump right into a problem and start talking about how to analyze a derivative and from that graph a possible graph of an original function from that derivative. So here's the first derivative. We can see it's just a horizontal line, y equals 2. So our analysis here, the value of f prime is always 2. This is saying the slope of the tangent line drawn to f is always 2. This means the graph of f must be a line with slope 2. It doesn't matter where its y-intercept is. So we just want to plot a line with slope 2. Okay, now that's one answer that'll work, but that's just a possible answer. We can move that up, we can move it down, it doesn't matter. But that is one possible answer for the graph of f that will give us this derivative. Our next one here, so the derivative, let's analyze this one here. The derivative is negative here, which means our original function should be decreasing. The derivative is positive here, which means our original function should be increasing. Since the derivative changes from negative to positive, right here, we should have a relative minimum at x equals 0. And because the slope of this line is always positive, that means the second derivative is positive. That means our original function should always be concave up. So we want a graph that has a relative minimum at 0 that's always concave up. So a possible graph might look like this. And same as before, we can move this up or down, anywhere along this, and that graph would be a possible answer for the function f. Third one here, f prime is negative, so our function should be decreasing the whole time, with the exception at x equals 0. At x equals 0, the derivative is 0. So the function is not decreasing there. All right, so we already know our function is always decreasing. The value of the second derivative would be positive here, so our function should be concave up here, but negative here, so our function should be concave down there. So we want a graph that goes concave up to concave down, but is always decreasing. And at x equals 0, it has a slope of 0. All right, one possible graph could look like this. Concave up, concave down. Slope of 0 at 0, and always decreasing the whole time. And again, that graph can be moved up and down as much as we want it to. Next one here, a lot of analysis on this one. The derivative is negative and negative. So on those two intervals, our function should be decreasing. And then we have positive and positive. So on those two intervals, the function should be increasing. Which means our original function here should have a relative minimum at -4, maximum at -2, and minimum at +4. Okay? Second derivative would be positive here, so concave up there, negative to about here, so concave down there, and then positive, so concave up there. All right, so this graph's going to look a little crazy, but they did give us a starting point for this graph. So negative 4, 2 should be on our graph here. Okay, and we actually said that x equals negative 4 should be a relative minimum, right? So maybe the graph looks like this to start with. And we should have a maximum at x equals negative 2. So maybe the graph goes up to negative 2 like that, and then comes back down. And it has a minimum at positive 4. So maybe the graph would look something like that. Again, this is just a possible graph. This is one possibility of many, of infinite possible answers we could have. Let's try to make this a little bit smoother here. That's a pretty good looking graph for a possibility for this function. Possible inflection points at negative 3 and positive 1. Look at our graph here. Looks like it changes from concave up to down there and concave down to up there. Next one, E. So the derivative starts off as negative and then switches to positive. So this should be a minimum here. It's positive, positive, positive until 1. But it doesn't change sign, so it's not going to be a max or a min there. And it's positive again. So the graph starts decreasing here, but then is increasing this whole time. Let's talk about the concavity. So the second derivative will be positive here up until about negative 3. So we should have an inflection point around negative 3. Negative until 1, so we should have an inflection point around 1. And then positive again. All right. So our possible graph, we need a minimum at negative 5, comma something. We're not told where this has to be. So negative 5, comma something would be a minimum. And it's going to be increasing the whole time after that, except at 1, it should flatten out. So maybe our graph looks something like that. So it's concave up, concave down, concave up as we go through it. With possible inflection points at negative 3, like we said already, and 1, like we said already. So it's concave up, down, and up. All right, next one. Derivative is negative and then positive. So this one right here should be a local minimum on the original function. The second derivative is always positive, so it should be always concave up. So this is actually going to look like the second one we did earlier today. Except at 1, we need to have our local minimum. The one we did earlier today had a local minimum at 0, I believe. All right. So if we take a look at this graph, we want it to be decreasing until negative 1 and then increasing after that. So maybe our graph would look something like this. So it's reading through our analysis there. F prime is negative on negative infinity, negative 1, so it's decreasing, and then positive from negative 1 to infinity, so that's increasing. The second derivative is always positive, except at negative 1, so the function's concave upward everywhere. This next part, I think I put that in incorrectly there. And it has a relative minimum at x equals negative 1, which we got, and it has no inflection points, which we got. Graph G. The derivative is negative, so our graph should start off as decreasing and switches to increasing, so this is a minimum. Positive derivative this whole time means the graph is increasing the whole time until you get to 3, so it should be a maximum, relative maximum at 3. The slope is always positive until there, and then negative there. So at 1, we should have a point of inflection. right? And it should be concave up until 1 and then concave down after 1. And this problem is actually telling us to go through the origin. So maybe our graph would look something like this, concave up and then concave down, with a local minimum at -4 and a local maximum at x equals 3. And our inflection point should be at 1, which my graph's not great with that there. Let's try to fix the graph a little bit there. So it should look something like this, and then switch. That's better. Now it looks like 1 is the inflection point. My previous graph kind of looked at it 0 as the inflection point, but now it looks better. All right, graph H. So we have positive slope, so increasing, negative slope, so decreasing. That point would be a relative maximum. The second derivative should be negative, 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 negative the whole time except at 1. Okay, so now we have all the information we need to graph this, right? We want to go up, 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 and then maximum, and then down, 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 down at that point. And there's not going to be any points of inflection because the second derivative here is always negative, so we should always be concave down. So this is really just going to be probably an upside down parabola, or at least something like that, where we have our local max at 1. The whole graph is always concave down, except at 1. All right, let's take a look at our next one, I. So the first derivative here is positive and then negative. So this point right here should be a local max on our graph. And then negative and then positive. So it should be a local min on our graph. So we know we have a maximum at 1 something and a minimum at 3 something. Okay. The slope of the derivative is always negative here, so that part should be always concave down. And then always positive here, so that part should always be concave up, which means there would be a point of inflection here, but there's no points. So that's not going to exist. There's not going to be a point of inflection at that point. So in reality, our graph is probably going to look a little bit like split parabolas, where we have a maximum at 1, so maybe it would look something like that, and then a minimum at 3, which you may have done something like this in your pre-calculus class. In the conics section, you might have drawn some conics that looked like that in that chapter. All right, last one of these, question J. The first derivative is always positive, except at -2. So the function should be increasing the entire time, except at -2. Okay? The second derivative is negative and then positive, so it should be concave down first, and then concave up after that. There are no relative extrema here because there's no change in derivative signs. And we should have a point of inflection at -2. So maybe our graph looks something like this. Concave down, concave up. Increasing the whole time. All right, so let's try to draw a couple graphs that have these characteristics that we're being asked to draw in here. First one says draw a graph where the derivative is always positive, and the second derivative is always positive, and f of 1 is -2. So f of 1 is -2. Okay, and the first derivative is always positive, so it's always increasing, and the second derivative is always positive, so it's always concave up. So we need to draw a graph that's always increasing and always concave up. How about that one? Looks pretty good to me. Second one, we have well, first of all, f of 1 is negative 1. So f of 1 is negative 1. The derivative is positive to the right of 1, negative to the left of 1, and 0 at 1. The second derivative is always positive. So it's always concave up. It should be decreasing and then increasing. And there's a possible sketch. Question C. Well, first we got f of 2 equals 1, so 2, 1. The derivative is positive to the right of 2, so increasing. The derivative is 0 for anything that's less than or equal to 2, so it should be a horizontal line. And the second derivative is positive, so concave up to the right of 2. So we want a horizontal line to the left of 2, and then an increasing concave up to the right of 2. On this one, we got f of negative 1 is negative 2, so negative 1, negative 2. The derivative is positive to the right of negative 1, so increasing. The derivative is negative to the left of negative 1, so decreasing. The second derivative is negative for all x. It's not 1, so the second derivative is negative means that this is always concave down. All right, we want to be decreasing to the left of negative 1 and increasing to the right of negative 1, but always concave down. That's going to look like maybe one of those old-fashioned birds that you drew back in second grade. Always concave down, decreasing to the left, increasing to the right of negative 1. All right, last two here. E. So we want increasing to the left of negative 3, decreasing between negative 3 and 1, increasing to the right of 1. The derivative at negative 3 and 1 is 0, and 0, 0 is a point on our graph. The second derivative is negative to the left of negative 1, and positive to the right of negative 1. All right, this is a lot to handle here, but we can do it. So first of all, we know we're going to have extrema at those 2 points. We want to be increasing, and then decreasing, and then increasing. So let's just try this and see if it works to how we want it to be. Increasing all the way to negative 3, and then decreasing all the way to 1. But it's got to go through. There we go. And then increasing after that. And we should have concave down up until negative 1. Looks about right there. And then concave up after negative 1. All right, last one here. We know f of 2 is 0, so 2 comma 0. Increasing to the right of 2. Okay. It's always negative 1/2 to the left of 2. The derivative doesn't exist at 2. And we're concave down to the right of 2. So this tells us that this is going to be a line to the left of 2 with a slope of negative 1/2. So down 1, right 2, or up 1, left 2. And then to the right of 2, we want to be increasing and concave down. So maybe it looks like that. Okay, that's it for our look into connecting the derivative and its graph together, the graph and its derivative together. Thanks again for checking out the video today, everyone. Have a good day.